Next up on coming attractions is direct air capture. So obviously we are talking about capturing carbon dioxide from the air. Why is it under coming attractions? Because it is still mostly in experimental stage, with some installations already doing that, but they are not at scale, and it's still not clear what the future is. But we know that for reaching our targets of 2 degrees and especially 1.5 degrees centigrade by 2100 with 66% probability, pretty much requires that we need to find a way to capture carbon from the air. Okay, so this is a carbon capture unit created by Global Thermostat. It uses amine. I don't know exactly how it's pronounced. Maybe I should learn that first. So it is pronounced as amine. In UK they would say amine. So it's a compound that is a chemical sorbent bonded to porous honeycomb ceramics that together act as carbon sponges. So basically you want air to flow through and rest of the air to get out, but carbon to precipitate out. It has to be done efficiently, absorbing carbon dioxide directly from the atmosphere or from smokestacks. The captured carbon dioxide is stripped off and collected using low temperature steam. The output is 98% pure carbon dioxide at standard temperature and pressure. Nothing but steam and electricity is required. This is another one, Climeworks' first commercial direct air capture plant based in Hinwil, Switzerland. The fans draw in the air where the CO2 in that air reacts with chemicals that selectively bind it. Well, I think you can imagine what the problem is. The concentration of carbon dioxide in the air is 0.04%. So you can imagine how many gigatons of air has to be cycled through to capture a sufficient amount of CO2, plus that CO2 that is then has to be washed out and stored or transported or used elsewhere is going to cost, let's say, some amount like $100 per ton, whereas already CO2 may be available much more cheaply for the various uses where CO2 is already required, which could be at $10 an hour. So you not only have to have the life cycle where the energy used to capture the air and to recycle the sorbent material, the sponge, the honeycomb, whatever, can be recycled and reused, and actually overall it is able to capture enough carbon, unlike the corn ethanol, for example. If you do a life cycle analysis on growing corn, converting it into ethanol, and then doing the transport and etc., the additional carbon it saves is really, really tiny bit. So this is something that also applies to direct air capture. So energy needs for DAC technologies or direct air capture technologies for CO2 use and storage in terms of heat or electricity. So liquid DAC storage, there is the heat and energy, electricity, liquid DAC use, solid DAC storage, and solid DAC use. So you can see that the requirements in terms of million tons of oil equivalent versus million ton of CO2 is a significant fraction. Of course, it depends on how well scaled it is going to be by the time we are doing really large scale and substantial direct air capture. Just to give an example of the uses of carbon dioxide, there are direct uses for food and carbonated drinks and enhanced oil recovery, where CO2 is pumped into the oil wells to push out the oil that's not easily going to be drilled out. And then there are chemical and biological transformations for manufacturing what are called synfuels or synthetic fuels, which are kind of the intermediate to the designer fuels. Manufacturing of chemicals and materials like polymers and plastics, organic chemistry and minerals. Again, the question is how much is going to be captured and at what price it's going to be available compared to other sources that are already doing this for a while. From the World Resources Institute, the status of leading DAC companies and the system types, so location Switzerland, United States and Canada, solid sorbent and liquid solvent. Thermal energy needs 80 to 120 degrees centigrade, 80 to 100 degrees centigrade and 900 degrees centigrade. So this is a thermal energy source, non-fossil energy source, geothermal, waste heat, etc. So the energy needed, the thermal energy needed to accomplish this DAC is non-fossil, which is a good way to start in terms of reducing the overall carbon footprint of the DAC itself. Energy resource agnostic, so right now it's not, can depend either on renewables or fossil fuels, and this is natural gas with CCS, so it is using a fossil fuel source, but it's doing carbon capture and sequestration, so it's a bit more complicated system. So here are the various projects, and this is the investment. So overall, the entire DAC business is suffering from lack of sufficient funding for research and installations, implementations, projects, and so on and so forth. So it's going to be a while. That's why it's under coming attractions. But as I said, looking at where we are headed in terms of the carbon emissions right now, and even including the agreements made and the commitments made under the nationally determined contributions and so on. I showed a figure in one of the previous podcasts. We see that already by 2020 we should have started drawing down carbon dioxide, which obviously we haven't started yet at scale. So we are on a very high emission trajectory, which has to change really soon if we have to meet the 2 degrees centigrade or 1.5 degrees centigrade warming target by 2100 with a 66% probability. If we reduce that probability, of course we can allow more emissions, but that's just not going to be a good idea to do that anyways.